Good afternoon, everyone. My name is Yuxiao. I come from Wuhan University, one of the most beautiful universities in China. Today, we will talk about a data filtering method based on agglomerative clustering. This is a joint work with Liu Jin. First of all, let us talk about motivation about our work. Software defect prediction is one of the most important software quality assurance techniques. It aims to detect the defect presence of new software models for learning from defect data. So far, many efficient software defect prediction approaches have been proposed, but they are usually confined within company defect prediction (WCDP). It works well if sufficient data is available to train a defect prediction model. However, it is difficult for a new company to perform WCDP if there is limited historical data. Cross-company defect prediction (CCDP) is a practical approach to solve the problem. It trains a prediction model by exploiting cross-company data and then applies the model to within-company CC data. However, the performance of CCDP is generally poor because of larger, irrelevant CC data. So the one challenge is how to weaken the impact of irrelevant CC data to improve the performance of CCDP. The ability to transfer knowledge from a source company to a target company depends on how they are related. The stronger the relationship, the more useful will be CC data. The performance of CCDP is generally poor because of larger, irrelevant CC data. Then we will talk about the existing approaches about cross-company data prediction. Here are three mainstream ways. The first one is to apply the data filtering method to find the best suitable training data. For example, Terhan proposed a nearest neighbor NN filter to select cross-company data. Peters introduced the Peters filter to select training data with the structure of other projects. They compared the filter to other approaches for quality prediction to assess the performance of the Peters filter and then found WCDP are weak for small datasets. The Peters filter and CCDP build better and more useful predictors. The source company data and the target company is usually heterogeneous. The heterogeneous CCDP HCCDP text is that the source and target company data is heterogeneous. Jin proposed an effective solution for HCCDP. They proposed a unified metric representation (UMR) for the data of source and target company and introduced the canonical correlation analysis (CCA), an effective transfer learning method into CCDP to make the data distribution of source and target companies similar. Results show that their approaches significantly outperform state-of-the-art CCDP methods for HCCDP with particularly different metrics, and for HCCDP with totally different metrics. Their approach is also effective. The third mainstream way is to apply unsupervised classifier that does not require any training data to perform CCDP. Therefore, the distribution gap between the training project data and the target project data is no longer assured. For instance, Zhang proposed to apply a connectively based unsupervised classifier that is based on spectral clustering to perform CCDP. So we will begin to introduce our approach. Our approach falls into the first mainstream way. This is to apply the date filtering method to find the best suitable training date. The main goal of date filter is to select the most valuable training date for CCDP model by filtering our irrelevant instance in CC date. In this paper, we propose a date filtering method based on algorithmic clustering algorithm, DFAC. DFAC consists of two stages. In the first stage, DFAC combines within-company instance and cross-company instance and use algorithmic clustering algorithms to group these instances. The main goal of algorithmic clustering is to partition WC instance and CC instance into K clusters such that instances in the same cluster are similar and instances in different clusters are dissimilar to each other. DFAC assumes that CC instances which are in the same clusters as W instances are the most valuable instance in CC date. Therefore, in the second stage, DFAC selects several clusters which consist at least one WC instance and collects the CC instance in the selected sub-clusters into a new CC date. Algorithmic clustering is an iterative process which measures current clusters continuously. It is possible that a certain cluster only contains one instance. Each instance is treated as one cluster at the beginning of iteration. In algorithmic clustering, instances are merged into clusters according to the distance between current clusters. We employ the average linkage method to define the distance of two current clusters. The average linkage between two clusters is defined as the average of distance between any instance pair between two clusters. Suppose that UA and UB are two current clusters. During the clustering process, the distance of two clusters DAB can be calculated by the following formula, where DAB, DA and DB are the number of instances inside the cluster UA and UB. DAB is the instance between two instances UA and UB. We define the difference UAB of the two instances UA and UB with the equivalent distance. Picture 1 shows the resulting clusters of a set of instances using the algorithmic clustering algorithms, where circle represents the CC instance and the triangle represents the WC instance. These instances are partitioned into three clusters by using the algorithmic clustering algorithm, namely CE, CR, CSAN. Take the cluster CE for example. Since the CC instance XE, X5 and X6 are in the same clusters as the WC instance X17 and X21, these CC instances are selected from the final CC training date. Take the cluster C2 for example. Since the cluster do not consist any WC instance, the CC instances in this cluster are discarded. The CC instances in the cluster C3 are selected in the same manner. Therefore, the final CC training instance consists of X1, X4, X5, X6, X7, X8, X12, X13 and X14. Then we will detail our experiment. We evaluate the performance of the proposed approach on 15 available and commonly used datasets which can be obtained from promise. The 15 datasets have the same 20 attributes, so we can apply all attribute information directly. Table 1 troubles the details about the datasets. In the experiment, we employ 3 commonly used performance measures, including PD, PF, and J measure. Probability of detection, or PD, is the measure of defective models that are correctly predicted within the defective class. The higher the PV, the fewer the false negative results. Probability of false found element, and PF is the measure of non-defective model that are incorrectly predicted within the non-predictive class. Unlike PD, the lower the PF value, the better the results. G measure is a trade-off measure that balances performance between PD and PF. A good prediction model shows the high PD and low PF, and thus leading to a high G measure. In order to confine whether DFAC can perform better than other data filtering methods, we compare DFAC with 2 state-of-the-art CCDP approaches. In every experiment, one dataset is selected as WC date, and the result regard as CC date to conduct the experiment. The CC date is considered as basic training date, which will be adjusted in every experiment. All date filtering methods are done on CC date, then processed CC date are used to build the CCDP model. Finally, the resulting model is evaluated on the WC date. The procedure will be repeated 30 times in every experiment to avoid sample bias. Then the mean values of performance are calculated. In this experiment, we choose naive bias as the CCDP model due to its effectiveness in defect prediction. The comparison results of 5 projects in NB class filter on PD, PF, and G measure are summarized in Table 4. The Table 4 shows that DFAC prefers better average PD and PF values than all the other data filtering methods. It shows that the NN filter often achieves good PD, but the worst PF, so it usually ends up with low measure value. The performance of DB-scan filter seems sometimes have lower PF value than the NN filter, but it has lower PD value. It is very clear that DFAC has lower value and a higher PD value than the other 2 data filtering methods. In the aspect of PD value, the DFAC approach increases the PD value to extent on most datasets. The PD value of 8 projects are better than others. On the most tests, DFAC achieves higher G measure than the other data filtering methods. In total, DFAC has acceptable PF value and can obtain better PD value in most experiments we conducted, and it most always achieves higher G measure values than other data filtering methods. In other words, the DFAC approach outperforms other methods, there it can be effective date filtering methods. Figure 2 shows the box plots of G-measure values for an n-filter, dbScan filter, and the DFAC with NB classifier on 15 projects. It seems that an n-filter approach always have low G-measure comparing to dbScan filter and the DFAC. Although DFAC has the same minimum with dbScan filter, the median values of both metrics of DFAC are higher than those of an n-filter and dbScan filter. Meanwhile, the maximum by DFAC is higher than by dbScan filter, but a little lower than that by an n-filter. In turn, DFAC has acceptable PD value and can obtain better PF values in most experiments we conducted, and it most available always achieve the higher G-measure than other date filtering methods. In other words, DFAC outperforms other date filtering methods. Okay, finally, we give our conclusions. In this paper, we propose a date filtering method based on algorithmic clustering for the CCDP. The method consists of two stages. In the first stage, DFAC combines WC stage and CC instance and use algorithmic clustering algorithms to group these instances. In the second stage, DFAC selects sub-clusters which consist at least one WC instance and collect CC instance in the selected sub-clusters into a new CC date. We conduct experiments on the 15 datasets to evaluate the performance of the proposed DFAC method. The experimental results indicate that the proposed method can effectively filter our fade out and weaken the impact of irrelevant data to improve the performance of CCDP. The proposed DFAC method is an effective data filtering method for CCDP. Okay, that's all. Thank you very much.